Good? Alright, we showed yesterday history of magnetism, how they first discovered and started to quantify magnetic effects. When you had a current set in this wire, it affected a compass. We'll see what that means in a minute. So when the current was turned on, the compass moved. When it was off, the compass went back to normal. Then down here, we shot a beam of what turns out to be electrons. We saw light they left because they were ionizing air. And we put a magnet over it, and the beam deflected. So we know again, there's something going on here with electricity and magnetism interacting. Next, 3 types of magnetism. You really don't need to know these for the read-ins, but they could be interesting for you. Ferromagnetism is a permanent magnet. So that's your standard, this sort of business. So these things are magnetic. You go near other objects, they behave like magnets. You stick these on your fridge at home. There are 2 other types, and these are not typically magnetic, but if you put objects in a magnetic field, they might behave like magnets. Paramagnetism is the most common. Paramagnetism is what you get when you put a paper clip. So a paper clip by itself is generally not magnetic. Take 2 paper clips, you hold them near each other, and there's no obvious interest. However, if you put a paper clip near a ferromagnet, what you'll notice is you actually get an attraction. So now it behaves like a magnet. So this is paramagnetism, and there's diamagnetism. I know in chemistry they talk a lot about paramagnetism, and they tell you this is not magnetism, right? I argue with Deneen about this, but you can actually inspire magnetism in materials that are generally not magnetic at all. This diamagnetism. These materials do not have any unpaired electrons, but actually this does work. I had it set up earlier. We'll come back to it later because it's not set up right now, and I'll show you. It's kind of like taking a charged object. Remember Bertha, and we put her near pieces of paper? If you take a charged object, put it near a neutral object, what happens? It attracts. Actually, with diamagnetism, you take a strong magnet and you put it near a supposed non-magnetic material, and you will actually get a bit of not attraction but repulsion. Okay, here's some common magnets. Permanent magnets. This is your standard north-south. Here's some fridge magnets. Kind of fun. It's kind of like these 2. You know, how do these stick to the wall? Well, little magnets in there. So the chalkboard also behaves like a paramagnet. Now, electromagnets are pretty cool. We have one over here. You can take a situation where the magnetism is generally weak. Take these 2. Now right now these wires are not hooked to anything. The battery may as well not be here. It's not doing anything. You bring these together, you get very weak attraction. Come, give it a test. Tell us. You notice anything?
Sweet.
A little bit. So there's something interesting you can do. You can actually hook a battery to this. Is nothing special. Your 1.5 volt battery. Derek did a good job, right?
I know.
Now, if you actually run a current around this magnet, so inside here there's loops of wire. We're connecting the 2 sides. So now we've completed the circuit. We connected the high and the low potential. And if we bring these 2 magnets together, at first it seems pretty normal. Let's try to center it. Derek, we need you again. You ready? Come on up here. Grab that rope. As long as this is hooked up. Let me now pull it off with the rope. I'm going to undo it real quick. Keep a hand on that rope. Let's redo it. There we go. Alright. Start pulling. Pull. Pull!
Oh.
This thing is not coming apart.
What?
Now, probably what happened there, actually it was still connected. We might have actually yanked the battery out. But it took a lot of effort, correct?
Yeah, it's a lot.
It took a lot of effort to get this thing apart. So here all we did is we ran a little current, not broken, we ran a little current around the magnet, and basically here, this is what we call an electromagnet. This is what they use at scrap yards to pick up cars. Bring down, this is very large, this is a big warehouse. You bring it down the frame of the car, you run electricity around that thing, and the magnet becomes extremely strong. Thanks. Magnetic awareness, okay. We did something like this. Do you remember the slide like this we did in electricity? Yes? Alright, they know about each other. Next. How do they know about each other? Anyone know the answer?
They're in the same field.
There you go. He said the field. In fact, yes, fields. Remember, if there's a smell field, you put a nose there, you can sense it. Temperature field, you put a thermometer there, you can sense it. Same thing with air pressure. Alright, next. There you go. It's a little bit of a boring slide, but a useful slide. Go ahead, one more. Alright, 3 fields we have to worry about now. Fundamental fields. Electric field, gravitational, magnetic. This is the new one. Now, particles play or exist in these fields. Go ahead. Now, if a particle has charge, just by having charge, it will be able to sense and respond to the electric field and also influence it. If a particle has mass, it will be able to sense and influence the gravitational field. And if a particle has charge and is also moving, and that's somehow connected to what we did before, with the current in the wire and what you saw coming through this tube, if the charges are moving, it will actually get involved with the magnetic field.
You have like no battery.
Uh-oh.
And it's still going, but yeah.
Alright, you tell me when it stops. That's okay. So, can these 3 things happen in one particle, or does this have to be 3 different particles? Can one particle actually have all 3 properties?
Yeah.
And therefore be influenced by and influence these 3 fields? Of course, you take anything, a proton, an electron, which generally are moving, and it will, all 3 of these will be true. Go ahead. Finally, one more. Forces travel through the fields. Get this thing out of the way. So the electric force, of course, will go through the electric field, the gravitational, and the magnetic. Go ahead. Not going?
No.
Just click on the screen again. There you go. So they'll go through the fields and they'll push on those particle properties. Now the gravitational field in this course, the only thing we worry about is masses, but actually you'll learn if you ever do some more relativity, you'll learn that things without mass can also be influenced by gravity. Go ahead. Alright, so here's similarities. You have 2 types of electric charge. There's 2 types of maybe what you want to call magnetic charge, but you don't call them plus and minus anymore. Plus and minus are distinct from north and south. They're not the same thing. People mess this up all the time. Probably when you were children you learned this the wrong way. Plus and minus and north or south have nothing to do with each other. Don't think that, oh, north is like, it's not. Separate. Go ahead. Now, something similar is that we can find the direction of the field around them, and it's different depending on which pole, just like depending on which charge. Remember who we used?
Posi.
You used posi over here. Look at this field. This is correct. Take a guess. Posi has a friend. Who are we going to use on this one? Is he right?
Yeah.
Is he right? He's right. Northy. You put Northy over here and you notice how it'll behave and how it'll behave. Don't be surprised, by the way, if you ever bring up Northy or Posi with anyone from a different school, they'll probably have no idea what you're talking about. Alright, anyway, if a charge is moving, you actually get a very interesting magnetic field around it. We'll talk a bit about it, but you won't be tested on it here. Alright, so both E and B, that's electric field and magnetic field, depend on charged objects, so you can have them at the same time. As long as this charge is moving, you have the electric field due to its charge, and the moving charge, you get the magnetic. Go ahead. Now here's the difference. Can you have positive by itself? You can have a proton. You can do all sorts of situations. You set up positive by itself. Can you have negative by itself?
Yes.
Can you have north by itself?
No.
No. South by itself? No. Those are called magnetic monopoles. Some theories predict them, but as of now, people have looked and spent a lot of money on it, and no one has found them. So, as far as we're concerned, these do not exist independently. This is because the behavior of magnetism actually comes about based on atomic and electronic interactions here. So basically, your magnet needs to be made of atoms and electrons, and the way they align with each other and the way they interact will basically give you this phenomenon we call magnetism. So it's not the same as charge. Go ahead. When you break a magnet, can you break it into a north and a south? No, it's like one of those horror movies. You break a magnet, you know what you're left with? 2 magnets. You break the 2, you know what you're left with?
4.
More magnets. In fact, all of our good magnets, part of the reason we have the cardboard between them here is because when they hit each other, especially these and all this other random stuff on here, they break. But the broken pieces, here's a little broken piece, is still a magnet. You still get your north-south on there. That's it. Pause.